I'm gonna try to make this interactive for the rest of the talk because obviously this is a talk about CMake, so I need to keep you entertained because, well, CMake. All right, so the title of this talk is Modern CMake for Modular Design. The idea, the basic idea is to use the build system to help you design better code. Let's start with a quick situation. And if at any point it looks familiar, you can like nod or even laugh, depending. You start with a project which looked like something like this at the beginning. And after several years, if you still look at the dependency graph, it starts looking more like this. Okay, you're probably at least some part my audience, giving the results. Yeah, it's terrible when that happens, and even against the best of us, it still happens today. So the idea of this talk is to first introduce you to modular design if you are not familiar with the concept, which I did not invent. It's something that I derived from the talks and books of John Lakos, mostly. After that, we will talk about build systems a bit. CMake is an illustration here. Technically, all of them, or maybe not all of them, but some of them at least are able to do the same thing. So even if you don't use CMake, you should be able to take something out of it. And of course, we'll see how do we combine that, which may seem a bit strange at first, like how my build system can help me design better code. That will be explained. So my name is Mathieu. You might have watched my previous talk yesterday on API and ABI. I'm a senior developer at Murex. I also became a contributor to Conan, so I, well, dealt a lot with package management, build system, that kind of stuff. And of course, I love portability, and if you want portable build in C++ today, usually you go for CMake. You can find me by email, by Twitter, or at my blog, which mostly talks about build system today, but will probably evolve over time. So let's talk about CMake. First, again, show of hands. Who knows CMake here? Okay, keep your hands up. Second question, who likes to write CMake files? Oh. I would have said more than expected, but no, not really. Okay, yeah, of course. It's, well, I guess most of us will find that our time could be more spent for doing more useful stuff. I don't know, refactoring, trying some new technology, even maybe watching a talk, I don't know, whatever else. But it has actually some good sides. First of all, it's not a build system, which is not a good or a bad side, but it's just some clarification. It does not build anything. CMake is just what they call a build system generator. Basically, it generates build file for your system that you can then build with your native tools, which are usually Make on Unix or Ninja, and by Visual Studio or possibly NMake on Windows. It's 17 years old now, which is well, almost of voting age. It's used by many projects. I mean, most projects you could find today on GitHub or somewhere else, I've cited a few here, are using CMake today. And I also know that lots of companies internally also use CMake. And CMake was like the promise that we could be able to build the same thing with both Windows and Unix with the same description, which, as most people know, works kind of, because, for example, if you try to invoke CMake on Linux, you do, on Windows, you do something like this, and on Linux, you do something like this, which I would argue is not really portable, but hey, it gets us there. And what's modern CMake exactly? Because, you know, modern C++, modern this, modern that, at some point, it's a bit hard to tell what it is. It's not a term I invented, again. It's something I took from a few blog posts that started to appear maybe 2 years ago, something like that. If you want to see another nice talk on that, Daniel Pfeiffer then gave something that you may have seen at CPP now. which is pretty nice to see the overview of what the recent version of CMake have been able to do. And one of the biggest ideas is that the paradigm of CMake has shifted seriously between the 2.8 dot something and the 2.8.12, because that was the first release when you actually had all the tools to be able to finally do some modern build. For example, there is less difference between 2.8.12 and version 3, which might seem a bit counterintuitive, than between 2.8.0 and 2.8.12. Because they changed the version scheme between 2 and 3. The 2, it's not a patch release, the last number, it's also a feature release, whereas it's become a patch release in the version 3. So there's actually lots of changes. And so, how do I know that a given project is not using modern CMake? Well, it's easy. I open the CMake list, and on the top it's requiring 2.8, not 2.8.12, not 3, not whatever, no, 2.8. Yeah, it makes me kind of sad because CMake, it's not only that you don't use the new features, it's that if you had them, CMake actually switches to compatibility mode and they behave differently or they are not even able to work correctly at all. Because there is some kind of backward compatibility settings to support some old patterns that we don't really want to see anymore. So what's modular design? Again, like I said, it's not something I invented. It's something I took mostly from the talk that John Lakos did. I think it was 2 years ago now, no, last year maybe, at CPPCon, which is a small talk of 3 hours and like 900 slides, something like that. It's a good watch if you haven't done it already. And probably a nice overview of his book, which is even bigger, on the matter of how do you design better code at large scale and still have some nice architecture out of it. I don't have, like I said, 3 hours to give you an introduction, so I will try to do that in maybe 10 or 15 minutes. So I don't think John is here, but John, if you're watching this, I'm sorry, I'm gonna have to take shortcuts, so sorry for the mistakes. Let's take an example, because I think it's gonna help you see what I'm getting at. Let's say you want to create an application, you join a small startup which is here to provide a taxi ride calculator. You're thinking, okay, that's the new thing. I want something, a small service that gets the best taxi ride I can get from getting from point A from point B by comparing the different fees that some companies are offering, Uber, whatever you have in your country. So it's just a startup. You just want a prototype to show your investors that you have a pretty nice algorithm that's very cool and that should get you funding. So you don't need much things. Just split it in 4 modules. First one is simply about representing the prices that you can get from the various people, the market prices, basically. The second one is the order, which is what your clients actually want to do, like he's named John and he wants to go from A to B, something like that. And maybe he has some preferences on the quality of the service, like he wants like 5-star, or he don't care, he just wants the cheapest. Whatever. And the next one is the fare, which is technically the output of the first 2, which is what can you offer him based on the order and the taxi prices. Does that design sound okay to you? Show of hands. Who thinks it's cool? Okay, not many people. That's not really what I expected. Well, for a simple algorithm, I think it's kind of okay. You have tried to keep a separate concern, which is what are the 2 inputs you're trying to represent? What's the outputs you're trying to represent, which are all business objects with some internal logic. And on top of that, you have your very cool patented algorithm, which needs the first 2 to output the third. You can test all in isolation. Like, for example, you want to test that the invariance of your taxi prices, client's order, or fares are okay without the rest. And then you can grab all 4 to test your nice algorithm with some the price you generated by hand, just to see if it's okay. All right. Let's say it's a sensible design. So that's cool. Your startup has got some funding. Investors are convinced. You get very better price than everyone else, very fast. That's genius. All right, so now they say, okay, you got some funding, but we want to be able to connect to something, because like you're just like constructing objects from a demo executable. That's not what we want. We want to be able to connect to market service prices and probably have something that we can output for our clients. So the next step is to go for serialization, which is probably what everybody in this room likes to write. So first, okay, the prices come from the market. So you need some way to serialize them from JSON. So you add a JSON library and you build a serializer on top of the prices. The idea is that you want to keep constraint separated again. Your representation of a price does not need to know about JSON. You only need to have a library that's able to combine both from one side to the other and possibly in the other side too. Client order, all right, you want to save that in the database for auditing or something like that. So you get a dependency on a SQL library of your choice. And same thing, you create a serializer on top of it. Again, the idea is to keep constraint separated, and I have a thing that you can test in isolation. Notice that, for example, I can still test my taxi rides without a database or without a real JSON input. I can just still execute my little algorithm and see what comes out. And okay, we do the same thing for the first serializer because we expect that it's going to be like a web service that's also going to have to feed some JSON. Okay, that's cool. Investors are okay. You have some serialization. That's cool. Okay, let's scale a bit. And then you want to create the real service. So you add some REST or HTTP stack. And on top of that, you plug it to your service, which is able to request your markets, serialize the price they get from the JSON, call your algorithm from that, save the order on the database, and at the end, output something in JSON format that your nice GUI can render, because obviously it's 2017, so you're going to make a web app. Okay, why not? Again, I think it's a sensible design that should be quite okay. But the problem is, in practice, from what I see, it's not what happens. Or maybe it's what happens at first, but then things go wrong. For example, you start having things like that, which is there is a cyclic dependencies between the order and the verb, because I don't know, somebody thought that there was a link that was more serious than expected. For example, you say that, okay, the fare is attached to a client, so obviously there is a dependency between those two. And then the HTTP needs JSON for some reason, we don't exactly know why. And maybe your taxi ride calculator is taking some shortcuts and directly calling the taxi price serializer, and possibly even vice versa for some strange reasons. I've seen that happen. And am I the only one to have seen something? No, I guess not. All right, so when you look at your library, you realize that, well, there are not two, actually. There are only one, because if there is a cyclic dependency, unless you can break it, it's, in terms of design, it's just one, because none can work without the other. So you can just say that your component is actually a taxi ride calculator and price serializer, which starts to sound a bit weird. And then you have a client order and fares. All right, orders and fares, they are kind of similar, so maybe it makes business sense to have them both in the same class or maybe in the same library. Why not? Okay. And then you continue, and at the end you got this. Okay, that escalated quickly, I agree, but that's something you can see in practice. You have a big taxi ride service and maybe a few third parties. And if you're lucky, they don't cycle between themselves. Yeah. I see a few people laughing. I'm sure I'm not the only one to have seen this. So what's the idea behind the book, behind the talks, is that you have to retain control of your dependency graph. You have to make sure, if you want to scale to thousands of, hundreds of thousands, million lines of codes, hundreds of libraries, you have to make sure that you're still in control of your dependency graph, that if you try to render the dependency graph of your application, you just don't get a big block because everything is strongly connected via a cyclic dependency, which it's, as we have seen in some feedbacks, what tend to happen over time. So you keep constraints separated, of course, because the reason why you don't want that big blob is that you don't want to initialize a full database of like 4 gigabytes before you can even run a unit test, because somewhere, sometime as a init function that you cannot mock or something equal. You also probably want to unit test without having a GUI. So it makes sense to have separated concerns. And then you can also reuse that, because maybe we get another project, maybe somebody at the company says, hey, actually I think the taxi ride algorithm is totally applicable to another type of service, so let's reuse that. Well, if it looks that way, you won't reuse it, you will probably just add the new service you want into that and probably have maybe 1 or 2 binaries in production that do both. And that's not exactly what you aim for. And of course, the idea is that really a module, if possible, should be reusable in other contexts at a minimal cost. Okay, so far so good. What's the relationship with build systems? What I call a modern build system, it's a build system that will help you do that. It's a build system that will help you keep control of your dependencies, that will protect you against anti-patterns of all kinds, which will, like, for example, refuse to build a cyclic dependency, or at least warn you that you're doing something very bad and that it should never go past the CI, that kind of stuff. So let's see, to explain what's exactly it's modern in a build, let's see what you usually do, like maybe what we did in the past when we build something. Simple example, we want to create a small project. It's just 2 libraries. We have a TCP library, which just is an implementation of the TCP protocol, quite simple, and a small TCP client that behaves more or less like Netcat. Very simple. What should the build file look like? Do you think it's sensible? Do you think it looks like a CMake file that you may or may not have written for that project? Yeah, I see a couple of people nodding. That sounds sound, actually, because, well, CMake, there's make in the name, so, well, your first reflex is to say, okay, that should be more or less like what have we done with make, just the name of the function or different. I call add subdirectory instead of make -c, that kind of stuff, but technically it's more or less the same idea, right? Yeah, more or less. The problem is, let's walk through it. First one, you say, okay, I have a sub-project, which is libTCP. Okay, that's sensible so far. I have a sub-project, I have a sub-library, I need that directory because it's a dependency. Okay, fine. You say, I have an executable, and the executable just is TCP client.cpp. Again, pretty sensible. That's just what you have to compile locally for your binary without dependencies. All right. Then you say, now I have to define my dependencies because else it won't compile, it won't find them. So you say, okay, but, well, the include directory is obviously under libTCP, so you go to TCP/include to say the dependency are there for the header files. Then you say, all right, yeah, I want IPv6 because that's part of the spec, so you add a -d IPv6 to make sure that the libTCP will be actually built with IPv6 support and that it will be visible in the header files because there's probably some if-def toggle like we all like. And finally, you say, okay, yeah, I must not forget to link because obviously, unless it's a header-only library, I know it's all the rage, but let's say it's not. If you don't link, well, it won't compile. So far, so good. Actually, not. Because the problem is, you did not really express a dependency to libTCP. You expressed build flags that happen to match the interface of libTCP. Basically, what you're doing is that you are mixing interface and implementation. Because what if libTCP decides that the flag for IPv6 change? What if libTCP decides that the headers are now this and possibly in another file? What if libTCP gets a dependency by itself? Do you add it there? The problem is that doesn't scale. Let's, for example, now we have a TCP, let's reuse it. Now let's put HTTP, and then let's do some kind of REST framework, because that's cool. All right, let's do that. Well, as you can see, you have a problem, because at the bottom level, your CPP flags are just minus ITCP, minus D, because you want to pay IPv6. Then you go for the layer up, so you put your own build flag, which are minus I HTTP, plus some define because you also want HTTP2, you want to be modern. And then, of course, you have to put back all the flags from your dependencies, and that goes on and on until your add includes and add include directories gets very big. So what do you do at this point? Well, if you have already seen my talk or a similar talk, you know what's coming. But if not, what I've seen, and I'm not sure I'm the only one, you just, well, since it's too physically hard to just propagate upward every time you change a dependency, what do? Well, you create a top file header, a top file, and at the top file you put all includes, all minus D, and even if you're a really bad person, even all minus else. I see some people nodding. I am not the only one to have seen it. Okay, all right, that reassures me. Yeah, that's not what you want to do. I think we all agree that's not good because that, for example, that means that anybody can include everything. Even libTCP could include librest. And possibly even it could work because you access just some types or maybe just some templates that don't need link time dependency. So even if you're just saying, okay, I'm just doing the includes, I'm not a bad person, I'm just doing minus I. What's wrong with that? I don't link. So it's not technically a circular dependency. Well, it is, because you're still using stuff from something that inherits from you, and that's going to end bad, because maybe someday someone will say, well, that was in line, but now it's not. Oops, doesn't compile. So the problem is, if you are trying to write build flags and more build flags, you cannot reason about them. It's just a chore. You just have to copy paste them from all your dependencies and hope, please, please, please compile, please, please. Oh, it doesn't. Okay, let's take those one too. Okay, yeah. Oh, yeah, it compiles. I'm not the only one again. No. Okay, yeah, that's the problem, because basically, you are trying to satisfy the compiler gods by sacrificing them build flags in hope that they will be appeased. And that's not what you should do, obviously. You should be able to tell you, okay, these are my dependencies. This is a module. This is another module. This is the relationship between the two modules. Can you reason about it? I think we can all reason about that. I mean, it's trivial if it's well-defined to parse CMake files or whatever build files, create a dot file like Peter and Kiki shown in their talk, and show the dependency graph. It's trivial. If you have to parse the flags, or even worse, if you have to parse the files, it's never going to end. And you won't be able to reason, or you will not be able to reason at compile time in something that your compiler or your build system could have warned you, saying, whoa, whoa, what are you doing here? I will not compile this. So a modern build system, basically, it will forbid you, or at least report problems like circular dependencies, because you actually talk to him in terms of dependencies and not of flags, so it can reason about it and can tell you, like, do some trivial analysis to tell you that something you're doing is not good. It will help you too, because when you are copy-pasting flags, most of the time, like I said, you have, well, you lose track of what exactly you're doing. You're just putting flags to make the problem go away. You're not exactly thinking, okay, am I doing something that makes sense? Like, why am I adding a dependency to an HTTP library, to an HTTP stack when I am building a TCP stack? Shouldn't that be the other way around? Well, if it's a flag with a big name, maybe you will catch it. But most likely, if it's 1,000 of flags, you won't. If you define a dependency, if you open a build file with a small project or maybe a big project and a library has like 2 dependencies, you can just look at the name and say, wait, that shouldn't be that order. Something is wrong. Why is my SQL library including the GUI? What am I doing? It's obvious. you see it immediately that there's something wrong in the design, that the code architecture is wrong and that something should be fixed. With flags, it's terrible. It's terrible, and most of the time it's even impossible. Basically, the idea of a modern build system is that it does more than installed. The thing with Make is that it's just a script. It's just, I wouldn't say it's a glorified bash because it does some more things, but the idea behind that is just, you run those commands, it will build, trust me, just run them. And that's what it does. Whereas, technically, what you should be doing is describing what you want to build and not how you want to build it. And from that, it should be able to understand what you're asking and telling you, no, this is not a sensible request. So in practice, what do? Well, first of all, you still define build flags, but you define them for your module and your module only. And what I mean is that only the thing that your module, without these dependencies, needs. It is like, okay, my private includes are there, my public includes are there, and if you pass me that option, that implies this, that I will need to compile. And done. That's it. You don't say anything else. Then you define your dependencies. You say, okay, my module A requires module B. And you keep out of other modules internal. You don't care when you need module B, you don't care how it's implemented, you don't care, like when you do, when you use a class, you don't care about the private bits, you just look at the interface. You just say, okay, I don't care how you do it in your CPP files, I just want you to execute this on that or that, take that request and give me the result. That's a similar idea. You just say, okay, I need that module. I don't care, and I certainly don't want to know how you do it. I shouldn't know. That's not my problem. And if the maintainer wants to change it, well, it's encapsulated, so he can, and everything should be fine. Of course, you have to specify everything in a matter of public or private, because as we've seen in the previous talk, that's a big difference. Again, for those who weren't there, public flags are basically what will be seen by the people who use you, because it's something that affects your API, your interface. So basically anything that is linked to your public includes, and anything that appears in your public includes. Whereas the other part, the private part, is what's linked to your implementation. How do you actually do the stuff you're exposing? And that's only a concern to you. It will not propagate anywhere. And of course, it's transitive. But you do not handle that. The build system handles that. You say, I require B. If B requires C, well, transitively, you possibly will require also parts of C because it's needed to build, but you won't care. It's not your problem. Like I said, it's public or private. For example, in the what I shown before, it was all public dependencies. So technically speaking, every time you have to, like in librest, if I need libHTTP, I will also get all the build flags for libTCP because it's a public dependency. So I would be able technically to include libTCP even if I don't directly need it. And most of the time, dependency should be private if possible, because as we saw, and as I think most of us know, everything that's implicit is dangerous. Because if you rely on something that's implicit, you shouldn't, but it's easy to forget. I've done it, you probably have done it too. If it's implicit, if it can just include something because actually through a dependency it's available, well, okay, it's fine, it compiles, it's good, you continue. And even most build systems won't be able to directly protect you against that. But what you can do is say, this is private. So nobody can see that it actually exists, and nobody can use that transitive dependency without explicitly saying, okay, I need that too, actually. So if you change that to a private dependency, like I've done there, you will see that at the top, librest doesn't see libTCP at all, because this is encapsulation. Okay, the idea is that the flags aren't gone. I just want to reassure the ones who think that I'm advocating for no flags at all. No, of course you still need flags. You just need to encapsulate them. You just need to say, this is the flags that I need at my level for my stuff. And when I say my stuff, again, it's what you directly have in your source files. Dependencies are not considered dependencies, are only handled through transitivity. So modern CMake. How many of you know that you can actually do something like that with CMake? Transitive dependencies with public, private. Oh, yeah. Maybe you've seen my previous talk, but I don't think so, because you would not be here. There is like a few other blog posts on that. And the idea is that it's actually possible since the modern version that I've said, like 3.0 or 2.8.12, if you really don't want the first version 3. I don't think you should, but technically maybe you have some constraints. The idea is simple. You still declare your module with add library or add executable. That doesn't change from the past. It's still always the same way. But anytime you need to declare something like a flag, you use target something. And of course, then if you need to declare a dependency or something, you use target link libraries. I know this is not very intuitive, very used, the thing that's basically the -L. I would prefer if there was like an alias that's called target depends or target requires or something that sounds like a real dependency and not just build flags. Unfortunately, there isn't. And actually, CMake is able to toggle if it starts with a minus, or if it doesn't understand the name of the dependency you're saying. You say, oh, okay, it's a build flag. Up, I pass it to the linker. This is not really good, and I wish they would fix that. But so far, that's the way you have to do it. And of course, every time you need to actually specify something, you tell CMake, is that public or private? For an example, first thing, you have to require a minimum version of CMake. I put 3.0 because that's kind of a minimum, but don't hesitate to go crazy. There are some nicer stuff that has been added in 3.2, 3, 4, 5, and all that, that could actually give even more interesting things. I cannot cover them all today, but do not hesitate to ask. I have a few things I can point you to. Then the first thing I do is that I broke my previous rule because I had a global flag, which might sound nasty. This is actually the exception that confirms the rule. It is that, oh, sorry. I think, and that's an opinion here, you might have the right to disagree, some flags should not be set at library level, because they affect everyone directly or indirectly. For example, compile flags. You might say, okay, compile flags, like for example, warning flags. You might want to say, okay, each module can have its own warning flags. That sounds like a good idea in theory, but in practice, what it means is that if somebody very high in the class hierarchy is more strict than you can actually break his build without breaking yours, which is kind of weird because your code is okay. So that's why I suggest that some things should be set at the top level and not at each project level, because if you diverge, that could lead to huge problems. But other than those flags, like warning flags, I won't even talk about IBI flags because that's another debate that should also be there or even not anywhere in the build system. But that's the only thing you should do here. Absolutely no include directories or things like that. Just possibly like warning flags. Then you add your library. Nothing's changed. That's the same way you always added a library in the past. If you didn't know, you don't even have to specify shared or static. You can do nothing, and there is a global toggle in CMake that you can use to control what kind of actual library you need. If you have a specific need, okay, say shared or say static. But I've seen lots of projects who actually don't really know which one they want, so what they do is set up a variable, like a dollar kind of a library or something. They expand it here, and they set up at the global level. You don't need to do that. CMake can do it for you. Then, of course, you define your module interface. So in this case, I have a public include directory, which is, well, name include, which is what my clients will see. And I have some private headers that I keep, for example, in the SRC directory. You may or may not want to keep them at the same place as your source files. You can change that. But the important part is that it's private. And then, instead of passing flags through to define compile options, you check options, because there is a setting, there are some settings in CMake that are basically variables, and you say, okay, what does the system requires? Okay, it requires that setting, like for example, my project is building with IPv6 support. All right, I need to activate this and that inside my library to be able to have it. In this case, I made a public setting, but possibly if the setting only affects your CPP files, you don't need to make it public. You can just make it private. And finally, you declare your dependency. So for each dependency, you do target link libraries, again, public or private, and just the name of the target. And done. If you have a header-only library, because again, that's something that it's quite popular these days, you can also declare it in CMake, even if it's not used, because you don't have to just say, okay, download that and point a -i against it. No, you can declare it as a target, even if it doesn't build anything. CMake has a keyword for that, which is interface. It's kind of weird at first, but it makes sense. First thing is, a library that is an interface library is actually a library that doesn't build anything. It's just something that you can, like a meter target or a handle target. You can also use the interface keyword when you want to say, this is something that my client should see, but that I don't need to build. 99% of the time, that means I don't build. Because if you try to do public here, CMake will complain like, oh, you're trying to set internal, you're trying to build something, and I don't have anything to build, so it will stop you. Just use interface, which means basically I don't build anything, but I want my clients to do that. You can even require dependencies. I don't know if you knew that. You can make a header-only library in CMake that has dependencies. It works. And of course, since you don't build anything, if your header-only library happens to require a static library, CMake will behind the scenes propagate the necessary -l to whoever needs them. It will work. So how do you recognize anti-patterns? That's easy. That's kind of stuff that you can now grab inside your build, your source directory, your project, and see if there's something wrong. First and most obvious is include directories. Like the big no, I don't want everybody to see that include, because that's breaking the first rule, which is only declare what you need and only declare what you do actually control. The rest is just transitive inclusion. So first, everything that modifies the global scope, like add definition, include directories. I have not seen many people use link libraries, which means every target should link against that. I don't think I've saw anybody do it. I think CMake actually gives you a warning because it's really deprecated, but just in case. Also, because you could say, oh yeah, I use target include directories, but then you put a relative path to something outside your source code. That's violating the same rule. You should not include something that's outside your scope. You should only care about your scope. Something I did not mention here, but that Peter reminded me about in the previous talk, that is, look in your code if people are trying to use include with quotes and some absolute path from the file system or some relative path, because some people apparently do that. My company actually banned include with quotes. You can only use includes with the chevrons, which kind of protects you against that, somehow. And I think that's a very sensible thing to do. You can actually use target link library without specifying public, private, or interface, because, like I said, they reuse something from the past, which was the way to pass the -l flag. if you don't specify it, it falls back to the old behavior and you don't get what you expect. You cannot actually tell CMake to warn you about it, which is a shame, but you can easily see with a basic grep on your CMake list or something that nobody used that in your code. And of course, don't use target compile option to set flag that change the ABI, because you will get incompatible binaries. If one project decides to change to 64 bits and another one says, no, I'm 32 bits, that's a caricature, but that's something that could happen, you will get a problem. So do not change the compile flags for one specific module. And that's it. With that, you get, like I said, about 90% of modern CMake. If I stop there, you should already have, I think, lots of things to do when you come back to your home. I actually had some feedback when I've given that at CPPCon. People told me that they went back to their CMake list and they say, oh my God, I can't look at my code anymore. I have to do something. And with only those tools, I think you already have something to process. I saw some people already nodding. I think they're already taking notes. That's pretty good. Thank you. Can I get a time check? Yeah? No? 20. Thank you very much. Okay, but since we still have some time, there is more. So let's go beyond. Because CMake is cool, but it's only one build system out of, I don't want to count. And there is the rest of the world. There is your project, but you probably have third parties, because even it's a pressing issue in the C++ community, we try to use other libraries. And I think I can name two that almost everybody includes in his project, which are gtest or something like that, and boost, because that's the two most common that most people have. Unless you have probably your own testing library, you probably won't do, or something that's quite similar. So the first thing you want is require an external package. I'm not saying you want to install it, just it's installed somewhere, you want to use it. How do you do that? Well, you know find package, I suppose. Yeah? Okay, great. So you do find package, like for example gtest, and then you create your executable and you say, oh yeah, I need to add gtest to the include directories to be able to include gtest.h. Then I have to link with gtest, of course, which is set by this variable when you find package gtest, because if you don't link with gtest, it won't work. And you also have to include threads. Who knew that? Okay, that's two people. The rest of you will have a problem on some, okay, maybe not anymore, but for example, on C++ or 3, on Linux, and all Unixes, if you don't put threads, it won't compile, because gtest behind the scenes requires threads. And since the find package does not, or did not endorse transitivity at the time, you get compile errors. It's actually written in the doc. The doc says, if you use gtest that way, find package threads and put them at the end. Done. Well, I guess in my case it works. On my machine it works. I'm using Windows. Yay, no pthreads. Okay, but even with that, it's wrong. Anyway, can you tell me why? Come on, I just said. I just saw it. Just.
Definitions. We need to
no, that will be actually works. Remember, we are using something. We should not be telling CMake how to use it. I want to use gtest. I don't want to know how to include gtest. That's not my problem, and that shouldn't be, because if the threads change to boost, I don't want to change my build files to also add boost.
The problem is that gtest has ABI changing macros.
Yeah, and that's another problem that we can discuss later. But no, my point here was that you should not fall back to the old pattern of, well, that's a third party, let's set the right flags for it to work. No, because actually CMake thought of that and fixed the problem. You can actually, since 3.5, do find package gtest and say gtest gtest, and that's a target. And since it's a target, you get the build flags, you get the dependency if your platform needs it, you get everything. Done. That works. You're using projects. You're using targets. And Actually, they have tried to add more and more because, you know, CMake has a few fine packages that they provide directly when you install it. And that's one more reason to actually upgrade your CMake, because as you can see, they added some of them and they patched, more exactly, they patched some of them in the recent version. 3.4 gives you OpenSSL, which is pretty useful, I think, if you want to do crypto. 3.5 have boost targets, and when I say boost target, you can actually require boost modules. You can say, I want boost.asio, and it will only give you the build flag for boost asio, and possibly the dependency that boost asio need. You can go that with gtest, of course, which I shown. You can get GTK and PNG, TIFF. More recent version have pkg config. And not like the pkg config binary, no. Like if there is a pkg config file of .pc on my machine, take that, make that into a target that I can include. Any library installed on your machine can just turn that into a proper target that you can just depend on, and done. So another reason to convince your boss that you need to upgrade CMake, because I actually saw people rejecting pull requests saying, no, I'm sorry, I can't use CMake.free features. No, there's no good excuse. Well, maybe there is, and I'll be glad to hear them if you have some, because I've done some upgrades of CMake, and from 2.8 to 3.3 something, and then later, and I had never had a problem. Okay, but what happens if you don't have a finder? Because, well, that's the most common, and there is even a support for pkg config, but maybe you're on Windows, and so pkg config, that's cool, but that only works on Unix. Or, well, technically that should work on Windows, but nobody uses it. Or maybe your library is simply not one of those. So what do? Well, there are some options. First of all, you can go to the maintainer and say, please, 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 make me a finder. That could be an option. But then again, if you are one of the maintainers of your projects, you also have to provide one for your users. So you're back to square one. How do I write a package finder? It's actually easy. It's even more easy than you think. You can ask CMake to generate one from the build information you do when you generate your binaries. I don't have the time to show everything from that, but Daniel Pfeiffer explained it in his talk, and it's pretty nice. And if not, well, you can do it by hand. It's like 1, 2, 3, 4, 5 lines, not including white space. You just say, okay, I want to find that library. I want to add an imported target. You say unknown because you don't know if it's static or dynamic, and CMake will automatically use the right platform extension to find out if there is a .a or a .dll or a .whatever. Then you say, okay, I want to include those include directory to be part of the interface of the module. And if you have a dependency, you can also express it like it. Easier than I thought? Well, actually, not exactly. It's a bit complicated. Not much more complicated, but for some strange reason, the syntax is actually more complex. First of all, you cannot just specify the import location directly when you do add library. For some reason, it's a property that you have to set by hand. And same thing, the target macros, for unknown reasons, don't work with imported targets. They only work with target that CMake actually builds. An interface, which it doesn't build, but don't ask. And actually, there is no reason for that. And someone, I don't know if he heard me or if he had the same bug, but he actually made a pull request and fixed that a few months ago, or even before that, which is pretty cool, because in the next release of CMake, you will be able to do target whatever on imported location, and your finders will be even simpler. Pretty nice. Are there more alternatives? Yeah, there are a few. But as some famous mathematician that you may or may not know have said, it wouldn't fit in the margin of my talk, so I cannot explain everything here. Like I said, if you check out Daniel's very nice talk, he explains lots of things about CMake, lots of things that I didn't know about everything in CMake, from generation to automatic code parsing, lots of stuff that covers a very wide range of stuff for like 1 hour and a half because it's a CPP Now talk. Go check it. There's very good information in that. So let's try to summarize now. So what's a modern build? Well, basically it's keeping your flags to yourself. We want to encapsulate, so implementation only concerns you. It does not concern whoever else is using your code. You think in terms of modules. And you let the build system handle the rest. And CMake can do it, and they actually did not, I don't know if they invented it, or if it's the other way around, but for example, if you look at the more recent build system that we've heard about, like, for example, Bazel, or Buck, or even some other more, they have exactly the same ideas. You work with libraries, you define the library, and you use it in another context. You do not set flags. I don't even think they can set flags. I think you can just say, these are public includes, those are private includes. You cannot just even talk with compiler language. You can only talk with some description language that says, this is what I want to include. Translate that to the compiler, please. I don't want to care about the flags. For modern CMake, well, first of all, you need modern CMake, so you need a more modern version of CMake if you did not actually have one already. And the latest, the better. Use the target version of the macros. Always specify if a property is public, private, or sometime interface. And of course, link against targets to get the build flags. Now that they fixed the target, for imported library, the next thing I want is that they actually had an overload on target like library that actually makes sense and express what you intend to do, which is declare dependency. I wish something could be done. For external packages, well, if you can, just use the modern finders, because CMake actually has some of them, and they are trying to add more, so use them. If not, well, CMake can actually generate one from your build that you could probably package with your release or install when you install the library so that it could be reused by the next project. And of course, you also have the option of a package manager, but I will let the Conan guys tell you more about this, and there are other options if you don't like Conan. Thank you. Now it's time for questions. Don't be shy.
I would like to add a few things to the find modules.
Yeah.
So first of all, you forgot to put an if target around your find module, because if you find package your module twice, your build is going to break, and that happens in larger projects.
There is actually an option for that, which is find package handle standard args, which is a macro with a quite long name, which is a package, also a package, a module in CMake that you can use. And if you just invoke that line, it automatically inserts a double inclusion guard that bufferized whatever you have already found in CMake. And you can use that to make sure that not twice the find package is invoked. But technically, unless you have like dependency that also do find package, I would say that you should not have to do find package twice. Actually, I would even require you to say find package, put that in your top level CMake.
Yeah, actually, in more recent CMake version, they added include guards.
Sorry?
They added include guards in, I think, CMake 3.9. So that would solve the problem. And the other thing I wanted to add is there is a way to check if you're linking against a proper CMake target or are just adding a build flag, and that's just with : :
Yeah, if CMake shows in the label of whatever you are passing as target link libraries 2 colons, it says, okay, that cannot be a linker flag, so that must be a target, and if it doesn't find it, instead of just blindly passing it to the linker without an error, it actually stops and says something is missing. And automatically, I think it's not automatic. You have to create all your targets with colons in the names. I'm not sure it creates a default target. I will have to double check. Like if you use your project, your project, I'm not sure it's the...
Targets you can use : directly, otherwise you need to create an additional alias to your record.
Yeah, that's that's unfortunate. That would be better if it done it by automatically. The other option would be to have a new macro that automatically says that must be a target that cannot be a linker flag. Like I'm asking about, not target link libraries, which makes no sense when you are not actually linking but requiring a dependency. Any other question? All right. Thank you, guys.